Okay, hello everyone. In this presentation for Year 11 Physics, we'll be looking at the idea, the concept of potential difference. So the syllabus points that we're covering is just defining what potential difference is, which is the change in potential energy per unit charge, and then we'll be doing some applying of this particular formula, and then we'll be looking at how charge separation produces an electrical potential difference. So to talk about potential difference, let's look at that word potential. So if I held an object above the earth, we would say that it has the potential to fall, and as it fell, it would have the potential to do work, and as it falls, it goes from an area of higher potential to an area of lower potential. And we think of and this is a good analogy for when we look at electrical potential. When we have charge moving from an area of high potential to a low potential, it will do work, and we call that potential in electricity, we call it potential difference, or voltage that you may see. So if we have a look at this diagram over here to the right and focus on what we got here, we got this charge. Now this charge is a free charge, but it's a positive charge. Now it's next to this positive plate, and as we know, like charges will repel. So this charge will experience a force in this direction. And what you've got in the blue lines is what we call an electric field. Now that electric field is part of, or it's caused by the potential difference that's there. So that potential difference creates an electric field, and the electric field tells us in which direction a positive charge will move. Similarly, if I decide that I want to put a negative charge here, then that negative charge will experience a force in the opposite direction because this plate is negative, which means the electron will want to go to the other end. So those are some words that you may see. Potential difference, which is the change in the potential. So the electron being here would have more potential than if the electron was there, because essentially the electron can't go as far as if it were back here. So it's the same as if you raise a ball very high up in the sky, it can fall further, which means it has a higher potential. And other words we use are voltage, and you'll also sometimes see electromotive force, or EMF. Now the formula we're going to get you to use in Year 11 is this one here, where we say that the potential difference, or the voltage across 2 points, is going to be equal to the change in energy, or the work that potential might be able to do, divided by the charge that's involved. And this equation may seem a little bit ambiguous, but what it's telling us is that the potential difference will provide for us a certain amount of change in energy per each unit of charge. And we can illustrate that using this equation, or this example here. So let's just say that you have a 12-volt motorcycle battery. So if you put a voltmeter to it, it gives you 12 volts, and it can move 5,000 coulombs of charge. And next to it, we have a car battery. So a car battery is a bigger battery, which is this one here, and that battery is also 12 volts, but it has the capability of moving 60,000 coulombs of charge. So from this, we can actually just easily figure out how much energy each battery will be able to produce. So have a go at that, pause it and have a go at that, and then I'll see on the other side. So let's start off with the bike battery. If we say that the work done by the bike battery is going to be its voltage multiplied by how much charge it's able to move, then we can say that that's just going to be 12 times 5,000. So the answer we'll get for the energy of the bike is 60,000 joules, or 60 kilojoules. Now, if we look at the car battery has the same voltage, but it can move more charge. So that would then mean that, what you should get is 720,000 joules. Now, this is the thing that a lot of people get a bit of a misconception about. Both of these batteries are 12-volt batteries. Now, the voltage, or the EMF, that each of these batteries offers comes from the chemical combination of that particular battery. The voltage does not tell you how much energy the battery contains. In this demonstration, we're looking at potential difference, or voltage. So to recap on what we did last week, or in the last session, if I connect a light bulb to the positive and negative terminals of a battery, I'm producing a current, because the electricity is going to be flowing, or the charge is flowing from the positive end, which is this end, through the circuit, and then into the negative end here. So the main concept I wanted to illustrate here was about batteries. So if I have a voltmeter, which is what I've got right here, and I connect it to that D cell that lit up the light bulb, you can see that it provides a voltage of 1.54 volts, right? So it's very easy to think that these other two batteries here, so I've got a AA and a AAA, that if I see what the voltage is on those, on this one I get 1.62, so I'm actually getting a higher potential difference. And what that means is this is a brand new battery, and that has a higher voltage than the bigger battery. So the size of the battery does not dictate what the potential difference across the terminals are. Now nominally, these first two should be about 1.5, but when you get them brand new, they're typically a little bit higher than that. And this one here at the bottom, this is a rechargeable battery. So its nominal voltage is actually 1.2 volts. But I think when I connect to it, because it's just been charged, it's closer to about 1.4 volts. And to even illustrate my point further, what I've got here is a button battery. Now this one is rated to 3 volts, even though it's very, very small. So if I connect the positive and negative terminals again, I get 3.19 volts. So this battery is smaller than these three here, but it outputs a higher voltage, which makes this really good if you want to, for being a 3-volt battery, it's the sort of one that goes in your electronics. So your CMOS battery in your computer, for example, or if you want to control some low-powered LEDs. However, if you were to connect this to a light bulb, it probably would be depleted pretty quickly. So the amount of energy that this battery stores is nowhere near as high as the energy in this battery here. So it's not the size that determines the voltage, but the size does give you an indicator of how much energy a battery will contain. And that's the demonstration on voltage. In the previous presentation, we talked about how you have charge and current. And now that we've learned a little bit about voltage, I can actually sort of paint a bit of a clearer picture for you. If I was to redraw a simple circuit where you have a power source over here and you have a resistor there. If the power source has a positive end there, a negative end there, what you've got is a build-up of positive charge on the right-hand side and a build-up of negative charge on the left-hand side. Now, just because we have a separation in charge, this is actually going to generate an electric field that goes from positive around to the negative. And this electric field is produced by the voltage, which is what this is producing. So this battery is the voltage source, or provides the potential difference. And that would mean that across this resistor, if I was to measure the voltage using a voltmeter, this measured voltage, assuming these are perfect inductors, which of course they're not, the measured potential across this resistor, since it's the only element in the circuit, will be the same as the potential that the battery provides. So the battery provides, we use the word EMF when we talk about what the power source provides. An EMF, or the voltage of say 1.5 volts, that would mean that the voltage across this resistor is going to be 1.5 volts, because effectively this is the only device that's actually using up that power source. And the diagram in the bottom right hand corner of the screen here sort of goes back to that gravity analogy. So if we have a higher elevation, so if we have say a whole bunch of water that's at 50, and then we pour it down a hill, what you'd find is that the water will run down that hill. So it goes from a higher potential to move to a lower potential. Once that water is at the bottom of the hill, it has no more potential to flow. And that's the same with the charges across the field. So if we look at, say, point A on this diagram, that might be something close to here on your flow diagram there. So point A has a higher potential, so the charge will flow around the circuit until it reaches the other end. And once it's arrived at the other end, so if this was point B, that would represent this point in terms of the potential. So when we talk about the potential difference, there's a lot of potential over here, and then it decreases as we go around the circuit to the negative side, where there is very little potential for a positive charge, for charge to flow. So just a quick question: if you have a current of 2 amps and it's flowing through a heater and it's flowing for an hour, and I can tell you that it's converting 1.7 megajoules of energy into heat energy. In other words, it's consuming, or 1.7 megajoules of energy has been produced. can you tell me how much charge has gone through that heater? So if I was to draw a diagram, I would have a sort of, and let's make the heater look like a coil, I don't know. And what the question's telling us is that the current flowing through this heater is 2.0 amps, and it's telling you that the energy converted is 1.7 megajoules, which is 1.7 times 10 to the 6 joules. So that's how much work has been done. So is that enough information for you to answer those two questions? So the first question is, what is the flow of electric charge? In other words, how much charge has been moved? And then from that, you should be able to tell me what the potential difference across the heater is. So the first part of the question is the net flow of electric charge. So if you remember from your previous presentation that the current is going to be equal to the amount of charge moving divided by time. If I rearrange that to get charge by itself, I know that it's equal to the current that's flowing through it times by the time. So to figure out how much charge I've got, I just get that current, which is 2 amps, and I multiply it by the length of time that it's been happening. And that says for an hour. So if it's happening for an hour, it would be 1 times 60 times 60. So 1 hour times 60 minutes and 60 seconds. And what you should get is 7,200 coulombs. And for part B, you would use the formula we've used so far, which is just the voltage is equal to the work done divided by the amount of charge that's gone through. And in that case, we know that the work done is the change in energy, which is 1.7 times 10 to the 6. And we divide that by the 7,200 coulombs of charge that have been moved. And if you did that, you will get 2.4 times 10 to the 2 volts. And that is the voltage across that heater. Okay, and here's your last question. If you have a 12-volt car battery, it runs a single 30-watt headlight. How many electrons pass through it each second? So, something that you may or may not know is that the power is equal to the amount of energy over time, and power is measured in watts, with energy is measured in joules, and time is measured in seconds. So that's probably a little bit of help. See how you can go with this question, and I'll see you when you're finished. Okay, so this question actually helps you out by saying how many electrons pass through it each second. So although it gives you a wattage, what this means is that you're looking at how many, you're looking at 30 joules being used up in that second. So there's the first part answered for you. So if you know that the voltage or the potential difference is equal to work divided by the charge, you can rearrange that to get Q by itself, where you'd have the charge moved is the work done divided by the potential, where you have 30 joules and the potential is 12 volts. What you'll end up with is 2.5 coulombs. That's how much charge have passed through each second. And now you want to figure out, if that's how much charge there is, how many electrons is that? So to find out the number of electrons, you simply put the charge in and you divide it by the charge of an electron. And what you should get is 1.56 times 10 to the 19 electrons, which is a lot of electrons. And that's all there is for this presentation. It's fairly short. What you need to do in this module is you're going to be combining your knowledge from charge and current and now potential difference to answer a few more of those textbook questions. Good luck.